So I do want to talk about some things here. I want to go back to the beginning of the year and kind of give you videos from then. So I want to make at least one a day that will help you refresh some of those skills that you learned in case you forgot it, or in case you're coming back from virtual, or in case you're just a future student of mine who needs some help with some of this stuff. But specifically for Algebra 2, FIFB3, you want to be able to graph functions expressed symbolically and show key features of the graph by hand and using technology. So graph square root, cube root, and piecewise defined functions, including step functions and absolute value functions. And then graphing polynomial functions, that kind of comes later. But we've been going over stuff like that, so graphing factored form polynomial, structuring graph. This also comes a lot from your Algebra 1 items. But what I want to get into today is graphing some of these functions and doing input-output tables to see why they work. So graph functions expressed symbolically, and then I think I'll take a look at Algebra 1 because we will eventually have to do this for Algebra 1 as well. So let me go ahead and switch the scene over to Algebra 1 standards. If you take a look here, you're also going to have to graph functions expressed symbolically and show key features of the graphs by hand and using technology. So in this case, you want to graph linear and quadratic functions and show intercepts, maxima, and minima. So that's specifically what we wanted to do. And so we're going to go back to the beginning and start to graph some of these parent functions. And so the first one that I want to start with is an easy one, and it's the constant function. So the constant function comes in the form f of x equals b, where b is some real number. If that's a little tough for you to think about, b is just a number. And so here's an example. Let's say f of x equals -7. So anytime you see f of x, it means the same thing as output. It's just in Algebra 1 and Algebra 2 and then so forth and so on in your upper level math classes. We start to name these functions something. So f, I think it stands for function, in some cases formula, that is dependent on x, okay? So anytime you've seen an x and a y table, it works exactly the same. And that's actually what we're going to use to start this off. So I'll do x and y. And anytime you see y, it also means f of x in this case. Now the reason why we start to change the formula for y in Algebra 1 and so on is sometimes you're graphing multiple different functions on the same coordinate axis. So if you're going to graph multiple functions, you're going to want some sort of system to be able to distinguish the two graphs. And so one system that we use is color. You'll see that. So I'll graph two different colors on one axis. And then another thing that you'll see is we'll name the functions different things. So one curve will be named f, g, another one will be named g, another one will be named h, that kind of thing. So you're going to see functions. And then you'll also see functions dependent on a context, okay? So if you anytime you see f of x, it's just a function, and you can actually do an input-output table for it and graph it. So that'll give you a feel for what the function looks like. It'll give you a feel for some of the domain characteristics, so we'll kind of go over some of that. So anytime I start a table, I'm going to start with some values that I know that are easy. So personally, I like to start with -3. Already with the mistakes. So -2, -1, 0, 1, 2, and 3. So if I plug in a number, I get back the same output here. And that's the beauty of the constant function. No matter what I plug into x, there's no x term on the right-hand side of the function to change the value of -7. So if I plug in f of negative 3, if I want to calculate this, f of negative 3, well, there's nothing to plug it in over here with. So anytime I plug it in, any x value I plug in, I'm still going to get back negative 7. So f of negative 3 is negative 7, f of negative 2 is negative 7, f of negative 1 is negative 7, and then so on and so forth. So what's interesting about this graph is that it stays constant, and that's why it's called the constant function. So whenever you look at it on a graph, what you'll discover, and what we're about to graph here, is you'll see that you get the same output. So constant functions are linear functions, but they don't have a slope. They have a slope of 0, that is. So what I mean by don't have a slope is they have a slope of 0. They have no change in y, only a change in the x direction. So if I take a look here, here's my coordinate axis, and I'm just going to do this in indigo because it's my new favorite color. So negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, and then negative 7. Okay? So I'm going to graph negative 7. And that's all the constant function looks like. So f of x equals negative 7 is an example, okay? So another example would have been like f of x equals 3. So let's do another one. So f of x equals 3 is another function. So if I draw the coordinate axis there, I can start to see that function, and I'll draw it in a different color so you can kind of distinguish. So if I have f of x equals positive 3 here, that just means that any input that I plug into x is going to give me back 3, okay? So if I plug in 0, I get back 3. If I plug in negative 4, I get back 3. If I plug in positive 5, I get back 3, and positive 6 as well. And so any point that I plug in, any x value, not any point, but any x value that I plug in, I'm going to get back 3. So for that function, I did it in green. So constant functions are going to have a straight line. So if you see f of x equals number, you find that number on the y-axis and then draw a horizontal line, a left and right line at that number. That is a constant function. Okay? Next function to cover is called the identity function. So the identity function is denoted as f of x equals x, and you'll see it as y equals x. This means the same thing. So if I graph any of those, if I put any of those on the board, or if you see any of those on a test, that is what it means. It means you're going to graph that function and do an input-output table. And so if I do an xy coordinate pair here, I'll do x, f of x, you can get in the habit of knowing that f of x means your output. Same as y whenever you get from 8th grade, or in some cases in Algebra 1, and then also in some cases in Algebra 2. So if I plug in any value, and again I like to start with like negative 3, all the way to positive 3, just counting by ones. And this changes depending on your context. Most of the time you'll try out numbers, and in some cases they will not work. So you just have to kind of play with these. But if I plug in negative 3 into x, I get back negative 3. If I plug in negative 2 into x, so f of negative 2, what you'll find is that on both sides of the equation, right, any value of x that I plug in for the function, that's my input, and then any value that I get back on the other side of the equation is my output. So if I plug in negative 2, the identity function is going to spit that back. So anything that's in this bin gets replaced and put over here, if you want to think about it that way. So f of negative 2 is equal to negative 2. So my input is negative 2 and my output is negative 2. And then f of negative 1 is my input. So I'm going to get back negative 1. F of 0 is going to give me back 0. So I just start to get the same value back and forth, and then I can start to graph this and visualize what this function looks like, okay? And so what's nice about this is whenever I start to visualize these functions, I can kind of play with their domain, their range. I can see what their details are, and if I see the equation, at some point, what I'm going to start doing is being able to see what that function looks like, okay, without even looking at it. So I know that when I look at f of x equals x, I get this line that we're about to draw. Personally, because I've practiced this, and of course I have a degree in this stuff, but it doesn't take a degree to be able to graph these functions and understand what they look like. So symbolically, once you start to get a hang of this and you start to see these functions and memorize these functions, you do get to start to get a feel for what the function looks like. So I'm going to do this in red. So if I plug in these points, -3, that's a coordinate. So I go left 3, down 3 from the origin. So always start at the origin when you're graphing. -2, -2, so I go left 2, down 2. -1, -1, 0, 0, 1, 1, 2, 2, 3, 3. And so I can continue that graph. I've got the pattern of the graph. Now you can continue graphing forever, right? The xy plane is continuous, but I want to get the feel for that function. So notice that it has a positive slope and that it just continues on forever. So it's a straight line through the origin, and so anytime I see f of x equals x, I know what the function looks like. Or I can do an xy table and see, or xf of x table, and see what the functions look like. So I can start to graph some of these functions. So let's do another one. Next function I want to talk about is the square function. Okay, and so I'm going to use f of x again and call it x squared. So remember, f of x just means y, and you'll also see y equals x squared. So over here, I can do an input-output table. And so when I do this input-output table, I'm going to start to plug in numbers. And again, I like to start at -3 to kind of get a feel for the function. And so anytime I start to graph these input-output tables, I'm going to go back and look at my function rule. So I'm going to start plugging things in and seeing what I get. So f of -3 is equal to -3 quantity squared. Anytime you plug a number or substitute a number in for x for an even power, what you want to do is you want to make sure there's parentheses around it. And I want you to get in the habit of doing that in case you're kind of uncomfortable with this at first. So the reason is because whenever you're squaring a number, you're writing it twice. And so if I'm squaring -3, that means I'm writing -3 twice and multiplying it by itself. Any square term, anytime you raise something to the second power, it means you're taking the term and multiplying it by itself. So -3 times -3, since it's written twice and multiplied, that actually equals +9, okay? So you've got to be careful on this, especially when you're typing it in the calculator. So if I go over here and I type in this function into the calculator, right, I get -3 parentheses squared. I do get back 9. But if you're not careful and you don't put those parentheses around it, you'll go to your calculator and you'll try and type in this number and you'll get -9. So what you'll notice is that if you don't put this -3 in parentheses, it's going to give you -9. It doesn't mean that math broke. What happens is the calculator thinks the only number you're squaring is the 3. The negative just comes along for the ride. So it's like saying, and you'll get the same answer in fact, it's like saying there's a -1 out front and then you're multiplying it by 3 squared. Whenever you type -3 to the second power, this is what it's going to interpret it as. -1 times 3, +3 squared. So you'll get -9. So get in the habit of multiplying those numbers and multiplying it by writing them twice or typing it in the calculator in parentheses and squaring them. So in square functions, you should not get a negative for just the regular square function, okay? So if I have f of x equals x squared, and there's no negative in front, and there's no other terms beside x squared, and you try and do an input-output table, and you get negatives, something went wrong for the y value. You need to go back and check your work. Same thing with f of -2 and f of -1. So I'm going to plug those in. You get back -1 squared, which is 1. -2 squared, sorry. That's +4. -2 times -2 is +4. And I was skipping ahead, so f of -1 is going to be -1 squared, which is +1. And then if I plug in 0, right, if I plug in 0 for x, I get back 0 squared. And then if I plug in 1, I get back 1 squared, which is just 1. And if I plug in 2, I get back 2 squared, which is 4. And then again, if I plug in 3, I get back 3 squared, which is 9. So, as I'm going with the colors of the rainbow, I'm going to start with orange next. And so, I'm going to go over here, graph this function. And I want to make sure I give myself enough room, so I'm going to do that. You stupid eraser. Erase! Thank you. So I'm going to continue this axis down, make sure I've got enough room. I think that's enough. Yeah, and we'll start to graph this. So there's my axis. So first thing I want to do, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're ready to graph. So this is the function space that I'm going to do. And so if I zoom in a bit, I can start to plug in these inputs and outputs. And let's look at that input-output table. So it's going to lag a second. Give it a second. Now it's starting to get it. So if you take a look at this f of x table, f of x table over here, the first input-output pair is -3, 9. Okay? So if I plot that with orange, right, I go left 3, up 9, and then the next thing that I'm going to see is -2, 4. So I graph that, so I go left 2, up 4, and then the next thing I see is -1, 1, so I go left 1, up 1, and then the next thing I see is 0, 0. So I plot that. And then on the right-hand side, you'll notice this symmetric nature, which we've talked about before, but I'm actually backtracking, so if you're watching this for the first time, don't worry about that, but you'll kind of see the symmetric nature whenever we graph this, right? I get 2, 4, and then 3, 9. I'm actually getting the same outputs, and that's no mistake. And then another thing to note is that whenever this function turns around, it's a smooth curve at the bottom. So if you take a look at the point at the bottom, it's called a vertex. So that vertex should be a smooth curve at the bottom. So that nice smooth curve. And so what you'll notice is that it kind of bends. So if you're not used to these types of functions, and maybe you're in Algebra 1 and you're watching this, not all functions are lines, okay? Some functions bend, and in this case, this is a quadratic function, and so it bends. So depending on the nature of the bend, it may bend up or down, and there's tons of things to study about it, but this is just a general quadratic, so this is called the square function. So it takes in inputs and squares them. So you can get a feel for what that function looks like just by graphing it, and you start to get some sort of this sort of visual relationship with structures of equations. So, right, if I have y equals x squared, and you've done this a few times and you've practiced and plotted the points, then what you'll start to see is anytime you see x squared, you know it's going to be a graph that bends up like that. So you'll know the general shape, and you'll know how to find these coordinates, and you'll know what that function looks like, and be better off in math for it, for knowing these functions. Okay? So let's go on to the next function that I want to talk about, which is the absolute value function. And he looks like this. Okay. So anytime I start to draw a graph, right, I want to do an input-output table. And this one's going to be pretty special. So if you're unfamiliar with those vertical bars that are around x, what it means is any number that I plug into this function, my f of x is going to spit out a positive. So we'll go with the same ones we've been doing. So if I plug in -3, I get the absolute value of -3. So those vertical bars just mean, okay, plug in the number and take the absolute value. And the absolute value means the distance from 0 on a number line. That's one interpretation. The other thing is just if it's negative, make it positive. If it's positive, leave it positive. So you'll kind of get the feel for it. But if you take a look at the number line over here, this is not a graph, but just at the number line. If I go to -3, and I ask myself, okay, what is the total distance from 0 to -3? What is this whole distance? Well, the entire distance, the positive distance of that is 3. I'm saying I'm moving 3 units, just 3 units. So it's the absolute value of the distance from 0 to -3, okay? So +3 is what I'll get back. Or if you like the structure of that, right, you know the absolute value of a number is the positive version. Absolute value of -3 is +3. So let's try another one, f of -2. Well, that's going to be equal to the absolute value of -2, which is +2. And then f of -1 is the absolute value of -1, which is +1. And then f of 0, well, what's the distance from 0 to 0? So 0 is neither positive nor negative, but there's no distance there. So if you think about, okay, you're asking yourself, what's the distance from 0? Well, the distance of 0 from 0 is 0, obviously. I hope that's obvious. I shouldn't say obvious, but I hope that's obvious. So the distance from 0 to 0 is 0. They're the same number. And then I start to see positives, right? F of 1 is equal to the absolute value of 1. Well, it just spits out positives, so anything that's positive already just becomes itself. So f of absolute value of 1 is 1. And then I can start to plug in these other ones. I know that absolute value of 2 is 2, and then absolute value of 3 is 3. So I'm going to start to graph some of these functions. So let's draw our axis here. So x and y. And what I see here is that, I'm going to do this in yellow. -3, 3 is a value, so that's that first coordinate up there. And then I'm going to start to draw the rest of these. So -2, +2, -1, +1, 0, 0, 1, 1, 2, 2, and then 3, 3. Now you might be looking at this and you might be saying, oh, that's just like the square function. It does bend up like the square function. It has a similar shape. But if you take a look at it, the most associated letter that's with the shape of the square function is a U. So it kind of looks like a U because it has that smooth curve at the bottom. The most associated letter with the absolute value function is a V. I'm not saying that it's equal to the letter V by some weird magical nature. I'm just saying that the structure of the equation makes it look like kind of like a V. So it's a good way to distinguish the two of them. So that is what the shape of that quadratic looks like. I mean, not that quadratic, but the absolute value function. Looks kind of like a V. And so anytime you see absolute value function, you kind of know what it looks like. And notice where it goes through. If I ask you to draw it on the fly, right, it goes through the diagonals of these graphs. So if I take a line through these diagonals, you'll start to see that they go through the diagonals here and here. And that's about all I wanted to say about it, so it looks nice and pretty. We're going to move on to the next function, which is actually your standard for algebra 2. Okay? So f of x equals square root of x. And we'll get into some of the other functions at another time because I'm kind of running out of time, but we'll go ahead and do the square root function. And so at this point, you might be kind of used to plugging in numbers. So you'll say, yes, we're just going to plug in the same numbers. So I'm going to do x, f of x, and I'm going to start with -3 as normal. That's what you might be saying. But if we take a look at this graphing calculator and we start to do outputs for it, so if I press second square and then type in -3, I'm actually going to get an error. And it's going to say non-real answers. And the reason is because you cannot take the square root of a negative, right? If you take a look at, let's do a few examples of this. So let me clear all this out. So if I do this square root of 4, you're going to know what the square root of 4, if you're familiar with square roots. You're going to know what the square root of 4 is. A square root is just two numbers. You're asking yourself a question. You're asking yourself, what two numbers multiply together to be 4 that are the same? And so if you could think of the factors of 4, you've got 1 and 4. Those are two integers that multiply to be 4, but they're not the same. So the other pair of factors is 2 and 2. So 2 times 2 is 4, and that's the pair that works. So anytime you type in a square root, you're trying to find, it's asking, what is the number that when I multiply it by itself equals 4? And the answer is 2. So 2 is the number that when you multiply it by itself, you'll get 4. Same with square root of 9. You'll get 3, right? Because 3 times 3 is 9. So what two numbers multiplied together, what number, whenever you square it, gives you 9? It's going to be 3. But if you think about it, what if I did square root of -9? Well, if you try the same thing that you did with square root of 9, if you try +3 and -3, they're not the same number. An opposite of a number in the number itself, they're not the same number. One is like having $3 and the other one's like owing $3. So anytime you try and calculate the root of a negative like this, it's going to say non-real answer. So in mathematics, it's helpful to study numbers like that are negatives underneath the square root, and in other cases we'll come back to that. But in this case, you're not going to graph that, right? We just want to graph the real part of this function. So anytime you're going to graph square root, negatives are out. So I want to talk about domain for a second, but it's something that's going to come back up in detail. But anytime you're graphing the square root function, x is going to be greater than or equal to 0. Okay? So any number that's greater than or equal to 0, you can plug into that function and get an approximation. Okay? So if I go over here, I'm going to start plugging in numbers. So if I plug in 0, let's see what we get back whenever we type the square root of 0. Now remember, the square root of 0 is asking a question. You're asking the question, what number squared equals 0? Well, the number squared, the number that is multiplied by itself to equal 0, is 0. 0 times 0 is 0. So that's uninteresting, but I get the same output. And then we're going to move on to 1. So we should be able to take the square root of 1. So we go back over to our calculator and we type in square root 1. And you're asking yourself what two numbers multiply to be 1 that are the same. And 1 by itself is 1. So that's another output. So input is 1, output is 1. And then the next number is 4. So I'm asking myself again, What's the square root of 4? What two numbers that are the same multiply to be 4? What number squared equals 4? Well, that's going to be 2. So my output is going to be 2 there. So when I plug in 4, I get back 2. And then I'm picking numbers that I can easily take the square root of. So I know that they're perfect squares. And by perfect squares, I mean that they have two numbers that are the same that multiply together to be them. So the next two are 9 and then 16. So I've got the square root of 9 is 3, and then the square root of 16 is 4. So I'll let you check that for yourself. So if I start to draw this graph, right, I'm going to need a longer axis. So kind of going with the convention, red, orange, yellow, green is next. And so I get 0, 0, 1, 1, 4, 2, 6, 7, 8, 9, 3, 10, 11, 12, 13, 14, 15, 16, 4. And so that's enough to kind of see what the function looks like. And you can kind of see this nice bendy nature. So this graph continues on forever. You can continue to plug positive numbers that you can take the square root of, but it gives you that nice shape. And if you're wondering, okay, what about the left-hand side of the graph? Well, we can't plug in negatives, so there's nothing that's going to be, there's no points that are going to show up over here. So we're done with this graph, and we're also done with the video. So if you want to see more on this, I would definitely watch the next video that comes out. That's whatever's in this playlist. There's a few more parent functions that we have to graph, and specifically they're pretty tough ones. So like cube root, exponential functions, which are a little dicey at first. That kind of thing. So we will get to that, but I want to, before we end, I want to kind of recap some things. If you graph these in the graphing calculator, so I'll show you how to do that. Let's say we're going to graph y equals x. I should get roughly the same curve that I put in for the xy coordinate plane, and that's what your calculator is doing. It's using code to take whatever you plug into it to approximate the function. So it's doing a bunch of input-output. So if you take a look, if I type in y equals x, I'm going to get that nice line, that nice diagonal line that we were taking a look at. So let's do x squared next. So if I type in x squared, I should get exactly the same or something very, very similar due to error, right? Because we're full of errors, we can make mistakes of this function. So if I type in x squared, I'm going to get that same graph. So if I take a look here at scene, if I type in, I want to make sure you know how to do that. So if I go to y equals, clear it out, I type in x to the second power, or x squared here, and I graph it, and it gives me this function. That's roughly the same graph we have there in orange, right? Roughly the same graph. And then we can start to graph in other functions. And you might be wondering, okay, what about absolute value? Well, yes, you can. It's just a little tough to find. So we're going to do that. If I go over here, I go to y equals. I clear that guy out. And then I go to math. Then I go to num. Absolute value is what I'm looking for. So that puts bars up there. So those bars go around the absolute value symbol. That absolute value symbol goes around to x. And if I graph it, I'm going to get that nice V shape we looked at. Now if you notice, the width between the x is a little bigger than the width between the y, so maybe if I kind of widened the window, I get more of a shape. I promise it's not off, so I'm actually going to pack some more terms in there so you can kind of see the same shape. So I just went to window and changed the window. You don't have to do this, but I want to show you, yeah, roughly, if I have the same amount of tick marks, the space between the tick marks, it's going to be the same. So you kind of see that nice shape. Okay, and then the next function I'm going to type in is square root, and the graphing calculator can also do that. So You might be wondering, okay, but why do we have to do the graphing calculator? I mean, why do we have to do it by hand? Why do we have to know what these functions look like by hand without the graphing calculator? Well, there's several reasons why you'd like to. One, right, it's good to have information about the functions that you're looking at. So if you know a general shape of a graph, you can kind of know some things intuitively about the graph before you start to do anything. You may not even need the calculator to even look at the graph and answer a question because you already know the shape of the graph. That's one reason. Another reason is this calculator is quote-unquote stupid, okay? It can only do what you program it to do. It's only as useful as the user. So if you rely on it too much, and let's say a test comes up where you can't use the graphing calculator, that's an issue on your part, okay? Because you don't know how to do it by hand, and it's especially buggy, right? What if your calculator runs out of batteries and you don't have any spares? This calculator is a tool. The most powerful tool you have is in your head, okay? So just make sure that you're using this to supplement that. So if you take a look, there's the graph of that function, and it's roughly the same one. Yeah, I'm satisfied with that. So I hope this helped. It's something that I wanted to do, kind of go back, cover some of this stuff that we've talked about at the beginning of the year, and show you some things, show you how much you've progressed. So hopefully this is easy by now if you have already started it, but if you're starting it in the new year, hopefully the new year is better, or the new school year is better, because right now we're during a pandemic, and I hope that this information is helpful to you while you're at home. You can always come back and look and use it as online notes, okay? And there was one last one that I wanted to graph, and you can graph the constant function. So if I didn't want to leave him out, so if I go back, I type in some number, I don't know, I can type in -7 like I did. You're going to see a vertical line at -7. And then also I could just type in 3. And so you'd see a vertical line there. And that's about all I wanted to say. Oh, sorry, I didn't get to do that. So I'm going to do that again. Okay, so if I go to y equals, the y equals key, and I type in -7, I can graph it, and you'll see it there. Then I can go to y1 again, clear all that out, write 3, and I'll get the same value. So if you take a look here, those are the same functions that we had to begin with. So the graphing calculator just does this for us, and that's helpful. So take it easy.